In this video, I introduce a Quasi-Newton's method for machine learning using Taylor expansion. Twice the differentiable function f(x) is expressed as here. This gradient and this hashing. To find x that minimizes f(x), namely find the solution to this equation, derivative of f with respect to delta x is equal to 0, namely this equation. Conducting the derivative above, we have the following equation for delta x. And then we express the delta x by using hashing and gradient. Using the equation above, the next position xk plus 1 can be computed iteratively in this formulation, where mu is a step size, hashing and the gradient determine the next position x k plus 1. However, Newton's method is time-consuming to compute hashing for high-dimensional optimization problems. Quasi-Newton's method defines B to approximate the inverse hashing in this formulation. BFGS is one of Quasi-Newton's methods to solve the equation above without computing hashing. First, we define two variables, y and k, in these two equations. The problem becomes a constraint problem, minimum subject to two constraints, which results in an updated equation to approximate hashing edge using the inverse B. We update inverse B by using this formulation. Updating inverse B only requires previous position and previous gradient. Using the definition, delta x is computed using the inverse B here. Linear search is used to find the mu, and then we update x k plus 1 using xk, mu, and delta x. BFGS method uses the following procedure to obtain the inverse B. First, we compute descent direction delta x, and then using linear search to compute the optimal step size mu. And then we use mu to compute x. Then update and store B. BFGS doesn't compute hashing, but it requires the extra memory to store B. This is the updated equation for B. Finally, use the Woodbury formula to compute the inverse B. For more details, please check with these references. Thank you. Bye.